We're going to talk a little bit about valence bond theory and the molecular orbital theory. Valence bond theory is essentially the electrons belong to each of the atoms that are bonded to one another, and they only share them. So there's sometimes they run into an identity crisis. And and we've looked at VSEPR, which is the way we determine the geometry of molecules based upon the valence bond theory. So if we use a Lewis structure for, say, ethene and ENE, we're going to talk about that in interchapter B in just a second, how to name these compounds. But we know that this is ethane, C2H4, C2H6, excuse me. That's ethane. And if we draw the Lewis structure for that, we know that each one of those carbons is tetrahedral. And what's required, let me go back to methane. Right. Methane is CH4. And do you remember drawing the electronic configuration for the different elements? We draw the configuration for carbon. It has 6 electrons, right? So we would draw the orbitals 1s2, 2s2, 2p6. So that would be the atomic structure. And this is what would have to go into making this molecule. Well, the geometry of s orbitals is spherical. The geometry of p orbitals is dumbbell shaped. Right? So they're not the same. But we know from experiment that methane is tetrahedral. And each one of the bonds that are formed to the carbon atom, they're all equivalent. They're equivalent in length, strength, and bond angles. And so we have to do something to fix that. And remember, I think I said something about this. When a theory goes wrong, what do? You can modify it, which is what we're going to do with this one. You can throw it out, right? Start over. You can restrict its use, or you can turn it into a religion. So what we're going to do here is take these two. This is called hybridization. We're going to hybridize these 3 orbitals. You should have 3 p's and 1 s orbitals, right? So we're going to hybridize those to give us 4 sp3 hybrid orbitals. And each one of these hybrid orbitals points to the apex of that tetrahedron. Okay. This was, Linus Pauling. Linus Pauling proposed this. And it's a fix for a weakness in the valence bond theory. Okay. So we know from VSEPR then, if we have this structure that we're given by this model, then these orbitals have to be hybridized so that we give 4 equivalent orbitals. So the number of the atomic orbitals that go in to make the hybrid we have to balance. We have to have the same number. We got 4 of these going in, 4 come out. Okay. So this is going to be an sp3 hybridized carbon. And 4 here, same thing, sp3, sp3. Now the hydrogens don't have to be hybridized because they've only got a 1s. That's it. So when we get to, if we take one of these, if we take this, turn that into a double bond and get rid of two hydrogens, right? So we have 1, 2, 3, 4, 1, 2, 3, 4, 2, 4, 6, 8, 2, 4, 6, 8. Each carbon still has an octet. Well, now we have three groups, right? Which have to be hybridized to give us three equivalent orbitals. So we would have sp2 hybrids, sp2 hybrid orbitals to give us what? Three sp2s yields trigonal plane. That bring back nightmares. Okay. So, and because this is a sigma bond and a pi bond together, if you have a sigma bond between two atoms, and our models will show us that, you can rotate that bond. Right? You can spin it till the cows come home. But if you have a double bond, you can't rotate it. That's what we're trying to show in this slide. This ethene molecule has to be trigonal planar here and in the same plane there. Right? You can't rotate the bond if it's a double or a triple. Now you remember how that bond was formed. Right? If you have sp2 sp2 hybrid bond here and sp2 here, what do you got left over? You've got a p orbital that's unused. Right? So you got a p going like that. This is an unused p orbital, a 2p orbital, unused. You get sideways overlap. That's where the pi bond comes from. Okay, and this is all based upon the valence bond theory. So once you do that, you can't rotate that bond or you'll break that pi bond. Okay. So what they're trying to show us is you can't write it the second way, the one on the right. It doesn't work that way. Okay. Covalent bond, all bonds are two electrons, and the valence orbitals, and this is all based upon valence. So we simply ignore that one right there. And we're working with the valence. Remember, the valence orbitals are the highest principal quantum number level. So this would be quantum number 2. Those are valence electrons. So we have, why did I do that? sp2. Yeah, I put 6. I totaled them all up and put 6 there. So we've got 2 electrons here, 2 here. They go into sp3, 4 sp3s, and that gives us 4 electrons. Right? 2 here, 2 here, 4 electrons go into those orbitals. And when they overlap with your hydrogens, you would have each one of these SPs, sp3s. Right? We could write them like this: sp3, sp3. Each one of those has 1 electron each. And then when the hydrogen comes in there with its 1s orbital with 1 electron, that's where we get the bond. Okay. And they share electrons by overlapping those orbitals. Okay, so I think this slide is trying to explain what I just talked about, where the s orbitals are spherical, p orbitals are dumbbell shaped, pointing to x, y, and z axes. Now, when we overlap hydrogens, it's very simple. You don't have to hybridize. It's just 1s from from one side, one s from the other side with their electron, they overlap and they make a bond, a sigma bond. So there's only one bond possible between two hydrogens. The diatomic elements are like that. And I shouldn't say that. Some of them are. The halogens and hydrogen are like that. Okay? So we would have hydrogen would be like this. What's another diatomic? Oxygen. Oxygen would be like this. Nitrogen would be like this. Fluorine would be like that. Then all the halogens follow suit, except that they overlap successively higher level atomic orbitals. And you don't have to hybridize any of these. Right? You don't have to hybridize any of them to get the bonds. This is the hybrid scenario. And a single bond is always sigma. And you have to have at least one sigma bond on axis. You can't have pi bonds without sigmas. But you can have a single sigma without pi's. You can only have one sigma because there's one axis between the atoms. Okay. So here's the hybridization of carbon for any alkane, actually. That's why carbons prefer 4 bonds, or 4, it prefers that octet. Now, it doesn't have to have it. I mean, we can force it to go higher or lower and give it a formal charge of a minus or a plus, but it's most stable when it has 4 bonds. Okay. Hybridization produces some strange things, and this hybridization is not just it may have been a creation of Pauling's mind at first, but in order to get his colleagues to agree to it, he had to do the calculations. He had to say, okay, the quantum theory says that this calculation will give you this probable distribution of electrons. So the hybrid orbital is going to have a big lobe on one side and a small lobe on the other. And those lobes simply mean their probabilities of finding electrons. So the highest probability of finding an electron in that hybrid orbital is wherever that purple is. And where it meets at the center is the nucleus of the atom. You're not going to find any electrons there. Okay. So this is the sp3 hybridization. And another way of expressing this is, since you've got one s orbital and 3 p orbitals, the s character for the hybrid orbital character is only 25%. And since there are 3 p orbitals, the p character is 75%. So that should give you an idea of what the orbital looks like. It looks more like a p orbital than it does an s by that factor. Okay. And there's your methane. Okay. Let's see. Hydrogen chlorine atoms in HCl held together by a single covalent bond. Apply the, I got that stuck in the way. Let me move that out of the way. Apply the valence bond theory to describe the bond. What type of symmetry does that bond have? All right. Well, let's take a look at it. All right, this is our molecule, HCl. And if we draw the Lewis dot structure for this, let's just do it the hard way. I mean, start from scratch. You got one electron here. You got how many valence electrons for chlorine? 7, right? So you have 8 electrons that have to be positioned. All right. You use 2 of them up with that bond. So that means you have 6 left over. Hydrogen can't take anymore. So they all go on chlorine. Right. That's our Lewis dot structure. All right. 1 sigma bond and 3 lone pairs around the chlorine. Okay. What type of symmetry will that have? That's linear. Actually, the symmetry around the chlorine is what? The symmetry around the chlorine is tetrahedral. But the bond is going to make a linear molecule. So I'm not sure if that's what they're asking for. Okay. Yeah, that's right. Around the chlorine atom, all right, chlorine's going to have, let's see, what period is that in? 2, 3. It's in 3. It's in the 3rd period. So we're going to have a 3s3p. So the valence electrons are going to be 3s and 3p. So that's 2, and that means this has to be 5. Right? 7, 8, 9, 10. 17, right? Its atomic number is 17. Oh, there's one up here. Yeah, 17. So the valence bond is going to be made from up here. Well, we've got this p arrangement, right, for x, y, and z. And we've got like that, this, and we've got this one there. Well, if we've got 5 electrons, where are they going to go? Well, this one, this x can have 2, and this y can have 2, and that z can have 1. So the bond there is going to be between, say, the z. I'm just arbitrarily picking between that 1 and the 1s for hydrogen. Right? So we don't have to hybridize chlorine. We just use one of the p orbitals, and it works just fine. Let's see. Am I even close? Oh, we're in a different molecule. So we get the sigma bond here. And sigma bonds are stronger than pi bonds, simply because you've got overlap on axis, whereas with pi bonds you have sideways overlap, which is not as efficient. And that experimental data bears that out. Right? At least that agrees with the theory. Okay, what do we do with lone pair electrons if we have to hybridize a molecule? Actually, we hybridize an atom. Well, for this particular one, that's methanol, right? CH3OH. Yeah, that's methanol. We do have to hybridize the carbon to get those 4 equivalent bonds. 3 go to the hydrogen and 1 goes to the oxygen. How about the oxygen? Does it have to be hybridized? The simple answer to that is yes, it does. The oxygen is also hybridized. And the lone pairs go into 2 of the hybrid orbitals. So if we look at this molecule like they do, right? we've got like that, lone pair here and lone pair there. We've got 4 equivalent bonds here, which means this is sp3 hybridized. And we have 2 bonds and 2 lone pairs, which also makes it sp3 hybridized. And that gives us this nominal bond here of 109.5 degrees, but it's going to be less than that because these lone pairs, remember, they balloon. They put pressure on that bond. But they're both sp3 hybridized. Oh, we're on to a different molecule now. Sorry. All right. Okay, how about the double bonds come into play when you have sp2 hybridization and you have lone pairs, excuse me, you have unused p orbitals with electrons available. If there are no electrons available, you're not going to have any bonds formed. So in this case, we do have an electron from one carbon and an electron from the other carbon in unused p orbitals, and they overlap to make the pi bond. So we know from VSEPR that this should be trigonal planar. And we also know that with sp2 hybridization, the character would be 1/3 S character and 2/3, 33 1/3, 66 2/3% P character. Because the ratio is 2-to-1 or 2/3 for P and 1/3 for S. So we should see, maybe on the next slide, we'll see a slightly different. It looks a whole lot like an sp3, but it should be more S character. It should be more spherical. Maybe that small lobe should be a little bit bigger and the big lobe should be more rounded and closer to the node so that we get a more S character. But it still gives you a trigonal planar arrangement. So that's what an sp2 hybridized orbital looks like with the unused p orbitals. And it can take any one of those orientations. As long as you have the sp2s in the same plane and the p is right angle, the unused p orbital is right angle to the others, then any one of those works. And whether it's A, B, or C depends on the reaction. Okay. So this is nothing new. We're saying the same thing over again. We do get the sigma bonds with the hybridized orbitals, and then the extra p orbitals, each has an electron. See those arrows? Those unused p orbitals, each has one electron in it. And that's where you get the overlap for the pi bond. Like that. So this is a planar molecule. Okay. We've already mentioned this also. If you have a double bond, there's a sigma and a pi. That's it. That's your only choices. And the geometry is trigonal planar. Okay. If you have a let's see, a carbon atom has 3 single bonds and no lone pairs. If it's positive charge, we call that a carbocation. And notice that In this case, what type of arrangement do you have? What type of geometry do you have around that carbocation end of the molecule? It's trigonal planar, right? And the unused p orbitals have no electrons in them. So if we calculate the formal charge, right? If you calculate the formal charge for that carbon, whatever this is, it's got these two hydrogens on it. And actually you have that single bond. We're expecting it to be a positive charge and this to be sp2 hybridized. So what's the formal charge on that carbon? Well, carbon has 4 valences, and we have 1, 2, 3 available. Minus 3 equals plus 1. So that's where that plus comes from. Right? We calculate the formal charge. So whenever you have a carbocation like that, just think sp2 hybridized. And the p orbitals are empty. They're still there, right? And they can accept electrons. And my guess is that's where the reaction is going to take place. If a carbocation is involved in a reaction, it's going to involve those unused p orbitals. Okay, so if we look at a molecule that has, this is acetylene. This is acetylene. Or if you're in England, they call it ethine. ENE means one double bond, a double bond. YNE means a triple bond. We'll get to that in interchapter B in just a few minutes. Okay, so what do we have here? Well, we've got one group on that side, one group on that side. This has to be linear. How do we arrange that? Well, we only need 2 bonds on either side, 2 sigma bonds on either side. So that carbon has to be sp hybridized. Right? So we take the 2s and one of the 2 p's, and that makes an sp2 sp hybrids. One for this side, one for that side. And what's left over? You have 2 unused p orbitals at right angle to each other. Right? So we would have, say, we would have like this, we would have like this on both carbons. So we get an overlap of these, and then 90 degrees, say, in and out of the plane, you get an overlap of the other 2, and that's the other pi bond. So a triple bond is a sigma and 2 pi's. And the character for an sp is 50-50. 50% S character, so it's going to be more spherical than the sp2 or the sp3. And they're still not drawing it right. That looks like the same as we got before. And this is to show that the unused p orbitals are right angles to each other. Simply because the orientation of p orbitals is on the x, the y, and the z axes. So if you're only using one s and one of the p's, then you're on one of those axes, and the other 2 axes have the unused p orbitals. And there again, as long as the unused p orbitals are right angles to each other, and the sp hybrid is right angles to both of those, then any one of those orientations will do. And this is to show the overlap. You get an overlap in one plane, and then you get an overlap of the unused p orbitals in the other plane to give you the 2 pi bonds. So you've got an extreme electron density between those, on axis or off axis between those two carbon atoms. This is a very electron dense region. And well, that goes for double bonds also. It's more dense, electron dense for a double bond than it is for a single. And many of the reactions that occur because of those pi electrons. Hopefully we'll get a look at a few of those reactions in the future. Okay. So if you have sp3 hybridized carbon, or any atom as a matter of fact, sp3 hybridization always gives you tetrahedral structure. sp2 gives you trigonal planar, sp gives you linear. Okay, what about this one? What's the hybridization of each non-hydrogen atom in this molecule? How many total sigma and pi bonds are there? Oh, well, we can do that one. We can do the second part right now. So for that molecule, we've got this hexagonal structure with oxygen over here. Okay. And we've got a double bond here, and then we've got a there and a triple to nitrogen. Okay. That's a carbon. All of these are carbons right here. Remember, if you have a carbon here, it wants 4 bonds. So they're going to be hydrogens there. Just to help you. Oh, excuse me. That carbon's already got 1, 2, 3 bonds. So we only get 1 hydrogen there and 1 here. But we do get 2 here. Okay. That nitrogen doesn't have any hydrogens on it, because we don't assume hydrogens on nitrogen. They will always draw them in. So this is a nitrogen by itself. So the last part, they asked for sigma and pi bonds. How many sigma bonds are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 sigmas, if I counted that right. But everywhere you have a bond, it has to be at least a sigma. And then the pi bonds, the pi bonds are 1, 2, 3. Okay. Now we left out lone pairs. Well, since there's no charge on these atoms here, and this one would have to have a hydrogen on it, like 1, 2, 3, 4. Oh, I messed up. That should be 15. Because I left that hydrogen out. 15. Sigma bonds. The other question is, what's the hybridization on the non-hydrogen atoms? Okay. So we want the hybridization on this one and this one. Well, what do we have here? Well, we've got to have 2 lone pairs for that oxygen. And for this one, we have 1 lone pair. The easiest way to think of this in terms of oxygen and water, right? It has 2 bonds here. What's left over? 2 lone pairs. So that's why I put 2 lone pairs in there. I mean, we can go back to basics, but trust me. And then for this one, nitrogen is triple bonded to something else. Well, if we go to the dinitrogen molecule, it's going to look like that. So if you have 3 bonds of this nitrogen to something else, it's going to have 1 lone pair. So this is 1 group, 2 groups on either side. This is sp hybrid. It has 2 sp orbitals, 1 for the bond and 1 for the lone pair. This one, like water, has 1, 2, 3, 4 needed. It's sp3. Because there's no double bonds here, you don't have any unused p's. They all go into the hybrid orbital. So let's see if we got that right. All right, we're counting up. It's counting up. To see SP, yeah, SP, okay, in that top plate, and then this is sp3. Yeah. Okay, how about sigma bonds? We're counting up sigmas. It doesn't give us a total. Where's the total? I don't see one either. Okay, that means I'm right. I was right after I put that extra hydrogen in there. Okay, now we're talking about bond rotation. You can expect bond rotation around a single bond. That's no problem whatsoever. It's like a spindle axis, right? This end can go, this end can go like that. But double bonds do not rotate. Let's see. Anytime you get a pi bond involved, you don't have rotation. That's just a simple rule. The double bond and a rule of thumb, this is a good one. If you have a double bond, then the two carbon atoms that are double bonded to each other and their first constituents, that's what that orange thing is showing you, those are all in the same plane. Now, once you get past that, the part of that plane that's occupied by the double bonded carbons, then the rest of them can do what they want. Okay, this is an old terminology. And it works in many cases. Cis versus trans. Whenever you have a double bond and you have at least two different substituents, in this case, 1,2-dichloroethane, both of them are dichloroethene, excuse me. If you have chlorines on the same side of the molecule, they're cis. Right? If you have them on opposite side, like that, that's trans. And everybody's heard of trans fats are bad, right? Trans fats are bad. That's what they mean. The fat molecule, that one that we were looking at earlier with the double bond in the fatty acid, at that double bond in the fatty acid, it'll either be cis or trans. Now, they may not have shown it in that particular problem to emphasize that fact, but it would have to be one or the other, or it would have to be a mixture of the two. That's possible. That's old terminology. We're going to introduce a more modern version because cis and trans can fall apart depending on what the attached groups are. So we've got another way of identifying them that we'll get into. Okay. Does this one have two distinct configurations about the double bond? The answer is yes, because we have a chlorine. This is in the trans configuration. If you put chlorine up there where the hydrogen is and move the hydrogen down, now you've got a cis configuration. And we know that they're not interchangeable because that bond cannot rotate. Okay. There. All right. This is a fatty acid, alpha linolenic acid. In biochemistry, lots of times the naming conventions are based upon the uh, efficacy, which is easiest, or which is the most common version. So this alpha linolenic acid uh, would be in IUPAC terms would be a trivial name, and there's a systematic name for this molecule. But the systematic names, when you get molecules that big, the systematic names go, they just like they balloon. But you'll notice that this one has 3 double bonds, and they're all cis configuration, which means what's not written in there is the hydrogens. So when you get something like that, those 3 bonds, we're looking at hydrogens here, okay? Hydrogens there. We typically focus on non-hydrogens when we're naming cis and trans. So this would be one part, this would be this part, and that part would be cis with each other. All those bonds are cis. And that gives it a particular geometric configuration. And then, of course, you have the carboxylic on the end. Let me see, how many carbons are in this thing? 1, 2, 3, 8, 10, 12, 13, 15, 16, 17, 18 carbons. Now, the cis bonds molecules in fatty acids are produced from natural sources. We try to produce them in the labs. For some reason, we tend to always end up with trans. Okay. Oh, models. Let's see. Do we need to model these things? I don't see any value in modeling those. Right? We know that they're easy to see. You can spin and you can't spin with a pi bond. Uh, all right. That's just emphasizing the fact. If we have a double bond with one carbon on one side and double bond with a carbon on the other side, then the hydrogens that are out there on the ends are going to be right angles to each other. Okay, the short version is CH2 groups are perpendicular to each other. And you can see that very easily from a model. All right. So how do these 3 relate to one another? Hybridization, we've talked about bond characteristics and effective electronegativities. So what we find is that the carbon hydrogen bond lengths for let's put the series up here. Let's talk about them. If we have this molecule here versus this one, versus this one, we're looking at the carbon hydrogen bond length relationship, right? And the bond strength also. So what we find is this bond length here, if we compare these, the bond length gets shorter as we go here. CH short. Now, why would it do that? What's happening is this is effectively a proton, right? Because its electron is used up in this bond. So if we increase the electron density in here, this is more electrons than this one, then that's drawing this positive charge closer to it. So the bond length here gets shorter. That's the whole point of that slide. And we call that effective electronegativity. When we talked about electronegativity in the past, we were talking about individual elements, right? Like fluorine bound to hydrogen. Fluorine and hydrogen would have a very, this is about 4, and this is about 2.6 or 3, 4, 2.4, something like that. So this would be very polar that direction. But if we increase the electron density around here with our bonding, now we're talking about changing the electronegative, the appearance of electronegativity for that carbon with the bonds. Okay, that's why we have to stick that word effective electronegativity in there. Okay. This slide is redundant. We've talked about the S character versus the P character. So the closer we get, as we move from sp3 to sp2 to sp, we get more S character in a bond. And that also contributes to the decreasing bond length, because the p orbitals tend to stick way out here. The s orbitals are more spherical and closer in. So that is another explanation for the shortening bond length. Right, we talked about that already. All right, what are we going to do with this? In which molecule A or B do you think the carbon-carbon double bond distances are longer? In which molecule are the carbon-carbon bonds stronger? Well, we've got double bonds around carbons. In A, they're separated, whereas they're combined around the same carbon in B. So that carbon in B is going to have to be sp hybridized. It's going to have more S character. So the bond should be shorter versus the carbons around in A, which are trigonal planar. Right. So let me see if that satisfies. So with greater S character, hybrid orbitals are more compact. So the carbon-carbon bonds in B are shorter and stronger. Okay, if that makes sense. Okay. So up to this point, let's see, we're switching gears. We've been talking about the valence bond theory so far, and that's where electrons belong to individual atoms and they're only shared to form bonds. Now we're going to get to chemical communism, collectives. The molecular orbital theory says that the electron, once the molecule is formed, all those electrons belong to the molecule. They belong to the collective. And then we write a new set of orbitals based upon molecular orbital theory. Right? There are some similarities, and we use some similar terminology in constructing molecular orbitals. but it's a completely different way of looking at the chemical bond. It's based upon the wave function, and this still comes out of quantum mechanics. Right? It gives a formula, and there's a Greek letter they use. It's called they call it psi. Proper Greek pronunciation is psi. But if you're in a sorority or a fraternity, you're going to call it psi. This wave function, if we square it, that term in the formula tells us the probability. That gives you the probability of finding an electron in a given region. So it's an important part of the formula. Okay, so when we go back to forming the bond, we have to think of electrons in terms of waves. So I like to look at it this way. If we were just looking at a single atom, right, the Bohr model of the atom was planetary. Right? It had orbitals, and the energies were quantized. So an electron here, say for hydrogen, we'd have a proton here, and we'd have in this n equals 1, this would be the electron, or its ground state. And it could move to 2 or 3 or 4, whatever, depending if you put energy into it. But the Bohr model said that this electron orbits the nucleus. Well, if it did that, based on other facts that we know are true, eventually it would be changing direction, which means it requires energy to make it change direction. It would be bleeding energy. And as it bled energy, it would just spiral into the nucleus. Well, electrons don't do that. Right? So that's where the Bohr model falls apart. So another way to think of it is, think of the electron as a wave. And it's a wave at that orbital. And the only wave that'll fit is the one that gives you perfect amplitudes, perfect number of wavelengths in that orbital. Okay, so that electron is a wave, which means if two atoms come close to each other, those waves can interfere with one another. You discussed interference in remember that from general chemistry? Okay, constructive interference, destructive interference. Okay, so if you have constructive interference, you get an increased amplitude, which in quantum mechanical terms, that means higher probability. So you can get constructive interference of these, say these two waves are like that, right? The result would be something that's like this. Okay? But destructive interference would be like this. Add those together, and you get nothing, right? That's destructive interference. So we're making a big deal of this because the molecular orbital theory is based upon this wave mechanical approach to electrons and bonding. Okay, and let's see. So I'm gonna let me jump around a little bit and see what's coming. Okay, we talked about that already. Constructive, destructive interference. And the definition of a node. Remember that? In these terms, a node is where there's no probability of finding an electron whatsoever. The psi function drops to 0, to nothing. Okay, so then we get constructive interference, this wave in a rope, or destructive interference. So when we're building our molecular orbitals, we start with the atomic orbitals, if you recall, the number and type of atomic orbitals. And then out of those, we build molecular orbitals equal in number to the atomic orbitals that go into the procedure. Right? So we conserve the numbers of orbitals. Well, how do you do that? Well, as a matter of fact, the way you do that, if we say this is energy, and let's keep it simple. Say we have hydrogen. So we've got this 1s orbital for this hydrogen, and we've got this 1s orbital for this hydrogen right here. Those are atomics. If we combine them into the molecule, now we need two orbitals, right? So one orbital is higher in energy or destructive interference, and the other one is lower in energy or constructive interference. And this one is a sigma derived from the 1s's, and this is a sigma star derived from the 1s's. This is a bonding orbital. This is an anti-bonding orbital. That's how we conserve the numbers. We make bonding and anti-bonding orbitals out of these. And this is all mathematical. This is the quantum mechanical equations are modified to accommodate this new theory, this molecular orbital theory. Right? So if we have an electron here, an electron here, where do they go? Well, we use the Aufbau principle, and electrons go into the lowest orbitals first, and when they're filled, then you move up, right? So these two would go into this position. One would flip back the other direction because you can't have two with the same spin. Okay, so let me see if I'm going to steal my own thunder. Well, there's a name for this. It's called the linear combination of atomic orbitals, LCAO. And there's the artist's rendition of bonding versus anti-bonding. Anti-bonding puts a node between the hydrogen atoms. And that's what you would expect. I mean, it doesn't like the bond. It goes the opposite direction. Whereas you get an increased density in the bonding orbital between. And remember calculating the bond order? Remember doing that? Bond order is equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So if we have 2 minus 0 divided by 2, bond order for hydrogen, dihydrogen equals 1, which tells us that it should be a single bond, and it is. Okay, this should be review, I hope. Let's see, you guys, Concord and WVU, right? Okay, so I know you got it before because you took my course, but they should have introduced you to these topics at some point. Okay, so there's your idea for hydrogen. They constructed a little bit different, their diagram there. I like this better. Now, in any molecule, when you get this molecular orbital diagram constructed, the very highest one, the very highest energy level that is occupied by electrons is called the HOMO, the highest occupied molecular orbital. So in hydrogen, it's simply this one. And the lowest unoccupied is the one in the next energy level above it, the LUMO. Hang on to that thought because that's going to be useful when we start doing reactions. Now, there can be non-bonding molecular orbitals, and this is all based upon the quantum mechanical equations. Right? We don't have any non-bondings here, right? But you can put them, and they would usually be somewhere. Since these are identical, the non-bonding would be right there if we had one. but we don't have one and we don't need one. This can get really, really complicated, and I don't give my students in general chemistry a whole lot more than just diatomic molecules, because there's the easiest ones conceptually. When you get into polyatomics, then actually you're beyond my abilities. Right? I can't manage anything like. I would find myself hard pressed to do the carbonate anion without looking it up. Okay, still doing good. So there's the HOMO and LUMO definitions. I'm not sure what this tells us. Hybrid atomic orbitals, combined molecular orbitals, and valence bond theory. Okay, sometimes we find it useful to combine the theories, the molecular orbital and the valence bond theories. I think the best way to approach this is if we're going to investigate or propose molecular orbital bonding for any given molecule, we're going to stick with the valence electrons. I mean, recognizing that all of them go together, but really the ones that are involved in understanding the bonding and even calculating the bond order, you only need the valence, the atomic orbitals from the valence that go into the molecular orbitals. So that's what's shown. It's just the valence orbitals that go into the molecular orbital model. Okay, so let's see, sp2 and sp hybrid atomic orbitals. Okay. So this would, for example, we might have something like if we had an sp3 hybrid orbital. Well, you still have, okay, they're making a transition between the valence bond theory and the molecular orbital theory. The valence bond is on the left, molecular orbital is on the right. If you get an in-phase overlap, the sigma molecular orbital looks like the one on the right and bottom. Excuse me, the left diagram with the right hand lower, the sigma molecular orbital versus the sigma star molecular orbital. So the key there is that if it's a sigma star and antibonding, you got a node between the atoms. It's just that simple. Anytime you have two atomic orbitals shared in a bond, you're going to have two molecular orbitals produced. In this case, we have two atomic orbitals that are unused p's. Those are the ones in the valence bond theory that overlap to make the pi bonds. So how do they look in the molecular orbital model? Well, we have a pi molecular orbital and a pi star molecular orbital. And that still gives you a node between the atoms that are supposedly bonded. How about, let's see, we do dihydrogen, what would be another with a double bond? Say oxygen. Oxygen has 6 valences. So if we did oxygen here, here, and then we had the O2 for the molecule, then we would leave out the 1s's. Let's just erase these. And we would go to the valences. So what do we have for oxygen in the valences? Well, let's see. Oxygen is going to be 8, right? Yeah, 8. So oxygen with 8 would be 1s2, 2s2, 2p4. So we're going to focus on this one. We know that this one exists down here. but we're going to focus on a 2s orbital and how many p's are we going to have? Well, there should be 3 p's, right? So 2 p's with 3 sublevels, and they're at the same energy. And let me move this over. Make room. Make room for the molecular orbital. And let's move this one down a little bit. Recognizing that there's one S down here. Okay. How many do we start off with? Well, we have 2 here, that, and we have 2 here. Right? Obeying Hund's rule. Right? We can't pair up opposite spins until we get 1 in each of the degenerate orbitals. Okay, now when we put these together, these go to bonding and anti-bonding. Sigma from the 2s, sigma star from the 2s. Okay, and for this one, we get 2 of those come together and make sigma from the 2p. And let's see, oxygen is no ST mix, so it's going to be this one here, and I'm sort of squeeze myself together here. Sigma star 2p. And then in here we have pi, the 2p, and pi star from the 2p. Okay? Okay, so now we have 1, 2, 3, 4. 1, 2, 3, 4. And then we have 4 here. So we have, for this sigma, we have 1, 2, 3, 4. Okay? That's kind of scrunched together. If we draw it out shorthand, we've got a sigma from the S, a sigma star from the S. We have a sigma from the 2p. We have a pi from the 2p. We have a pi star from the 2p. And we have a sigma star from the 2p. It's easier to see it this way. And this is going to have 2 in it. This is going to have 2. This will have 2. And this will have 2. A maximum of 4, because we can have 2 suborbitals. And we don't even need these last 2. Okay, so if we calculate the bond order here, it's going to be, right, bonding 2, 4, 6 minus 2 divided by 2. So that's a bond order of 2, which is a double bond. Okay, and that diagram is looking at the source here from the p orbitals. Right? So we get, and it's overlapping these to make the pi bond. Right? So the pi bond has 2 electrons in it. The pi star has no electrons in it. So that one at the top is empty for oxygen. Okay. So what would ethane look like? Now we're getting pretty complicated now. Now we're going to have to use some rules of thumb. Otherwise, it's going to be out of my league. So we're going to need, how many sigma bonds do we have in this molecule? Well, we've got 1, 2, 3, 4, 5, 6, 7. We have 7 total sigma bonds. So that means we have 7 sigma bonding orbitals and 7 sigma anti-bonding orbitals. So far, so good? Okay. That means total we have 14 molecular orbitals made out of 14 atomic orbitals. How about this one? Well, we have 12 atomic orbitals here. If we look at 1, 2, 3, 4, 5, 6, it looks like 1, 2, 3, 4, 5, 6. It says we have 12 atomic orbitals. Oh, I left out the hydrogens. Right. So on each of the carbons, we have 1, 2, 3, 4, 1, 2, 3, 4. That's 8, 9, 10, 11, 12. So we do have 12 atomic orbitals, one from each of the hydrogens, and then 8 more from the 2 carbons. And if we combine them, we need to have 5 sigma molecular orbitals to bond with carbons between them and each of the hydrogens. And then we have 5 sigma stars to balance that out. And then we have a single pi and a single pi star. That's what we're saying. And if we add them up, we still have 12 molecular orbitals. Okay. How about the relative energies of the molecular orbitals? Well, it's safe to say that whenever you have a sigma versus a sigma star, the sigma star is always going to be higher energy. In chemistry, lower energy means more stable. Okay. Ethine says we have 10 atomic orbitals. So let's see, let's count them up. One for each of the hydrogens, and 1, 2, 3, 4 for each of the carbons. So that's 8 plus 2 is 10. Yep. To have 10 atomic orbitals, that means we have to have 10 molecular orbitals in the conversion. Now, where do they go? Well, we only have 1, 2, 3 sigma orbitals, right, between the hydrogens and the carbons and the carbons and the carbons. And that means 3 anti-bonding sigmas. So that's 6 of them. Now we have 4 left over that go into 2 molecular pi orbitals and 2 molecular pi star orbitals. It takes some practice. Remember what degenerate means in chemistry. Okay. It doesn't mean perverted. Degenerate means the same energy. I don't know where they came up with that one. So here we have a different mix. So let's see. What we're trying to do is simplify the procedure so we can use it. If we had to go through all the details of building this model for these more complicated molecules, it would take us forever. And chances of getting it wrong would be exponentially increased. So how many atomic orbitals do we have in this methanol molecule? Well, let's see, 1, 2, 3, 4 hydrogens. So there's 4. Carbon has 4, so that's 8. Oxygen has 1, 2, 3, 4, right, for the lone pairs. So 4 and 8 is 12. So we have 12 atomic orbitals going in. That means we need 12 molecular orbitals. So how many sigma molecular orbitals do we have? Well, there are 1 for each of the hydrogens on the carbon, 1, 2, 3, and then 1 for the oxygen is 4, and then 1 other one for the hydrogen. So that's 5. So we have 5 molecular orbitals in the bonds. We need that they're all sigmas. We don't have any pi's. So we have sigmas, 5 sigmas in the bonds. That means we have to have 5 sigma stars to balance them out. And that leaves 2 orbitals left over. Well, where do those 2 orbitals go? They're non-bonding. This is where we get the non-bondings. And I'm saying that the non-bonding orbitals are where the lone pairs go. Hopefully it'll start to make sense as we go. Okay. Now we're going to do interchapter B. Some more nomenclature. I've been using some of this nomenclature already, enes and eins, but these give you the rules. There we go. Alkenes, alkynes, and cycloalkenes and cycloalkynes. So that just means we're looking at molecules that have double bonds and triple bonds in them. We still determine the root of the compound. We're looking for the largest number of carbon atoms in a chain or in a ring. So, for instance, that first one down there, with this provision, it's the longest chain that has the double bond in it, right? We wouldn't go from the lower 2 carbons on the left and count 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. We'd actually go 1, 2, 3, 4, 5 because 5 has the double bond in it. So we've thrown you a curve again. So that would be 5 would be pentane without the double bond, pentene with the double bond. So the root would be pentene. We have a 4-membered ring with a double bond in it, so that would be cyclobutene. Without the double bond, it'd be cyclobutane, but with the double bond, it's cyclobutene. We haven't got to numbering yet, right? We're just trying to find the root. The last one is the longest chain with that triple bond in it. So we find that that's 6 carbons long. Remember, where we transition from the single line to the triple line, there's a carbon there. That throws some people sometimes, but there is a carbon on either side of that triple bond. So we have 1, 2, 3, 4, 5, 6. The longest chain with the triple in it is a 6-member. That's hexyne. So that would be the root for this one. Okay. Now, what do we do about numbering? We go to the end of the molecule that has the double or the triple bond in it. So in that first one, instead, we don't start from the chlorine side. We start from the side that's closest to the double bond. We have 1, 2, 3, 4, 5. So that'd be pentene. And it would be 5-chloropentene. Would be the first one. Let's see. The second one, the longest length in that one is 1, 2, 3, 4, 5, 6 would be hexene. And now we want to minimize the number. So instead of numbering from the left-hand side, we're going to number from the right-hand side to give that methyl group the smallest number possible. So that would be 2-methyl hexene for that middle one. I know the name's not given there, but that's what it would be. And then for the cycloheptene, and in this case, we start at the double bond is number 1 for the nitro. The nitro is connected to the double bond on the ring at number 1. So which way do we go from there? we minimize the numbers for the other nitro. So we go across the bond, 1, 2, 3, 4, rather than 1, 2, 3, 4, 5 around the counterclockwise. We go clockwise. All right. So we got to find out what the root is, and then we add the prefixes. So let's see if we can name this. I'm gonna give myself practice drawing it too. 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6 here. Then we have one here like that. We have 2 chlorines here. And a double bond, branched here like that. Okay, so the longest one with the double bond in it, we would have to start from this end and go 1, 2, 3. So it's either 4, 5 or 3, 4, 5, 6. So we're looking at this part as the root. Right? So this would be hexene, would be the root. And we would start numbering from okay. When you have a molecule that big, the double bond could be anywhere in that hexane chain. So we have to say, where is that double bond? So in this case, we would say 1, 2. It's 2 hexene or hex. Actually, some places say hex 2 ene. I think this is preferred now. Hex 2 ene. And this would be 3, 4, 5, 6. And that would be 4 dichloro. Actually, that should be closer. Dichloro. There's no dash there. 4 dichloro. Hex2ene. All right, let's see if I got it right. Okay, we found the root. That's the root. Okay, numbering 1, 2 there. Okay. Then at the bottom, I left out this group, didn't I? This is okay. This would be 1, 2, 3 carbons. So if this is 1, 2, 1, 2, this is a methyl group. So we have to include, let's see, we've got 4 dichloro as one side group. We'll throw that one out. And then we have at 3, we have ethyl as the longest group there with a methyl on it. And the methyl occurs at the 1. Well, actually, it has to occur at the 1 because if it occurred at the 2, it wouldn't be ethyl, it would be propyl. Right? So it would be redundant for us to say 1 methyl. It's just methyl ethyl. And they're saying 1 methyl ethyl. Why are they doing that? All right. I'll go with it. In my mind, that's redundant. But so this gives us alphabetical order. C first. So it's 4 dichloro. Then 3, 1 methyl ethyl. 1 methyl ethyl. Hex2ene. Now, do they say 2-hexene? No, they say hex-2-ene. Okay. So I was right there. We've transitioned from 2-hexene to hex-2-ene. Uh, your guess is as good as mine. Whatever IUPAC subcommittee is in charge of this decided it was better. They still adhere to the rules. It's unambiguous and non-redundant. So I would take issues with this one. I think that's redundant, but that's the rules. Yeah. Yes. Yes. I started from here because of the double. Yes. That took some work. Okay. Molecules with multiple double or triple bonds. Okay, we still have to establish the root, and the root has to have all of the double bonds or triple bonds in it. And then the numbering system gives us the first double or triple bond that's encountered first. So that bottom one, we could go from either the right or the left. But if we go from the right, that gives the branch too high a number. We need to minimize the branch number. So instead of, we would have to go from the left, right? Start from the left on the double bond and count so that we give that side branch propylpenta 1,4-diene. Okay. So let's take that one in detail. I think that'd be instructive. So we have 1, 2, 3, 4, 5, 6. 1, 2, 6. That. Yeah, this is a double bond. And then this one is a double bond. And that's all we have. Okay, so we're taking this one. Yeah, taking this one as our root right here. And we're starting numbering here, 1, 2, because that gives us this branch with the lowest number. 2, 3, 4, 5. And the ene numbers come in the middle of so there are 5 units here. So this would be, excuse me, pentene. But we have to split it here because we've got a diene. Okay? We've got to split it there. And then we have to say, where are the enes located? We go from the first carbon encountered for the double or triple bond. This one is encountered at 1. And this one is encountered at 4. So it's 1,4-diene. Penta 1,4-diene is the root. Now, what occurs at 2? 1, 2, 3. It's propyl occurs at the 2. So it'd be 2 propyl penta 1,4-diene. This is the propyl group attached at the number 2 carbon. So far, so good. Okay. Let's take the next one. Let's see. We've got a 6-membered ring. And then we've got a side group here, oxygen and methyl group. Okay. So where are our double bonds? They're right here and right there. Correct? Yeah. Okay. So we've got two double bonds, and we need to start someplace. We can start here, 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 here. We're going to start. Well, let's see. It's going to be a diene, and it's going to be a cyclohexa. Let's get that part in here. Cyclohexa diene. We just need the numbering system. So we want the carbon groups. If we start, okay, here's the question that occurs to me. If we started numbering here, we have to go across the double bond to get to the other one. That's required. Right? If you go 1, 2, then that encompasses this double bond. So if we start here, then that's 1, 2, and that decreases the number for this one. So if we start with this one, 1, that would be fine, but it would make this one too big because it'd be 1, 2, 3, 4, 5. It'd be 5. It'd be 1, 5 rather than 1, 2, 3. So the diene now has the smallest possible number set, 1, 3. Diene. That's why we started down here rather than on the side group. And then we have to add this methoxy on the end. Where's the methoxy? It occurs at 2. Yeah, ox. Cyclohexane, hexa 1,3-diene. Now you'll notice that methoxy is an ether. We used to name these something ether. We would say methyl cyclohexa 1,3-diene ether. But that's changed also. Okay. How about the next one? We want to tackle that one. We've got 3 triple bonds. So we start with a triple on the end. Yes. So we got a triple here. Then we got a single, and then another triple, then a single, and then another triple. Okay. And then another single, and then we have a fluorine here and a fluorine there. Okay. So we want to start wherever we get. Of course, we're going to include all these triples in this root. So if we start on this end, or if we start here, we can't start here because that doesn't include the triple bond. We have to start on this end because that's where the triple bonds start. So that's why we do this numbering system. Even though it makes the difluoro a 7, we still have to incorporate these with the lowest numbers. And we can't start here with 1 because we've got another carbon out there. And so the longest chain incorporating all the triple bonds includes that carbon. And we can't start 1 there because that's not a triple bond. So we have to start on this end. So we've got hep, 1, 3, 5. Tri-ine. And then we have the fluoros at 7. We have 7, 7 difluoro. There. Oops. That should be together. Difluoro. There we go. 7, 7 dichlorohept 135 triine. I'm sure there are a whole lot more, well, like this one, that could mess with your brains. Okay, so what's the IUPAC name for this one? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 6, 8. Yep. Got a double bond there, a nitro group here. And then we've got a double bond here. We've got a branch here, the double there. Got a branch here, back. So that's everybody. Okay. What's the longest? The longest chain that includes the double bonds. Let's see. I think it would be like this. I'm pretty sure we're going to include that. Yeah, because that makes the chain longer if we add these to the chain. Oh, can't do that. Sorry. Nope, can't do that. Because if we include that double bond, the chain ends there. Okay. So, but we can't include this one because the chain ends on that carbon. So that means this one has to start at 1. Okay. All right. So what do we have? Heptene. Hept something something ene. Triene. Right? 1, 2, 3. So we've got a 1, 3, 5. 1, 3, 5 triene. That takes care of the root. Now we've got a 6 nitro. I'm going to put that up here. 6 nitro. And we've got a 2 ethyl. 2 ethyl. And we've got a 3. 1, 2, 3. 3 propyl. Okay, alphabetical. The 2 ethyl comes first. 2 ethyl. Right? And then 6 nitro. And then 3 propyl. Hep 135 triene. That's what I think it is. So 2 ethyl, 6 nitro, 3 propyl, that's A. Hepta 135 triene. Okay, I misspelled. When do you add the letter A before the suffix? Oh, they anticipated my error. Because the multiple carbon-carbon one groups, the letter A is added before the suffix, so this is a heptatriene. Okay, that's just one of their squirrely rules. I don't see any logic in it. I'd be perfectly happy with hept 135 triene. But I don't make the rules. Naming E9s. So those that have double bonds and triple bonds in the same molecule. We got the root, and we use the root that has the root includes the ine. So there's a concept in organic chemistry called priorities. I think it's called priorities. The highest priority here is the triple bond. The double bond takes second stage. So the ine is going to go on the end of the molecule's name. The enes are going to come right before that. So when we establish the longest chain, we have to include both the ene part and the ine part. And that first one includes the whole molecule. Yeah, first one includes the whole molecule. The longest chain that includes both of them. So we've got 1, 2, 3, 4, 5, 6 That's a hex. Now, why don't they say hexa? Yeah, that's my question. Why don't they put an A in that one? Go figure. Oh, add the letter A immediately before the corresponding locator number. And add the proper multiplier prefix. Well, that doesn't make any sense. Well, octa, of course, that's part of the name. But hexa has an A in it. Go figure. I'm not going to be strict on that one because it doesn't make any sense to me either. Okay. So we established the numbering system. So the carbon double bond and the carbon-carbon triple bond groups are given equal priority unless there is a tie between the two numbering systems. So okay. So the first rule is we end the name with ein, and the next one is een, but now it's the numbering system. So if we start in the first one, if we start with 1, we start with 1 on the ene end of the molecule because that's the lowest number for the double bond, double or triple. We start from the other end, then the triple will be at 2. So we're going to start at the ene end of the molecule for the first one, and the second one we've shifted the double bond over 1 and the triple bond over 1. So now we start at 1 for the ein end. That's the difference between those two at the bottom. It's just the shift of the double and the triple bonds, 1 carbon to the right. Now that makes the numbering system reversed. So the number 1 carbon has an ein on it. And now the number 4 carbon has an ene instead of the 1 ene on one end and the 4 ein. How about that, let's see, 8-membered ring? Let's do that. That's an octagon, isn't it? That's a stop sign, isn't it? Yeah, that's a stop sign. We have this one, and then we have that, 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 that. 1, 2, 3, 4, 5, 6, 7, 8. There we go. So we have a double bond here, and we have a triple down at the bottom. That's going to put some strain on that molecule. Take no word for it. So we know we have an ein and we have a diene. And the ein is going to come at the root, ein and a diene. And we have a cycloocta. Cycloocta. So now the numbering system's required. Which one gives us the smallest numbering system? Wait a minute. Add the locator numbers immediately before. No, we have to do we need to break a tie? What if we started with, okay, they're starting here, 1, 2, 3, 4. If we started here, it would be 1, 2, 3, 4, 5, 6, 5, 6 rather than 1, 3. I don't get it. Are we breaking a tie? Maybe because we have 2 enes and only 1 ein, the enes win on the numbering system. That's what I think. So this is going to be 1, 3, 1, 1, 3, diene, and 6, ein. That's puzzling. I'm not sure why we started there, unless it's to break a tie and two ings beats a one ein. Thank you. Oh, I see what happened. I've got this thing in covering up some information. There it is. Okay. That just means you're paying attention and I'm not. All right. So now we're going to shift over to benzenes. What's so different about benzenes? Well, there's a concept in organic and biochemistry. If we have a straight chain like that, and we have alternating double and single bonds like that, what happens is they conjugate. These are conjugated double single bonds. What happens is the electron density is delocalized over those three, which stabilizes the molecule, lowers its energy. So we would have electron density in that region rather than isolated here and isolated there. Well, the next logical step is to take that 1, 2, 3, 4, 5, 6, take that molecule and wrap it around and make a 6-membered ring out of it. And if we do that and we conjugate bonds, now we get an aromatic. Benzene is aromatic, and it's even more delocalized because now we have, and sometimes you'll see it represented like this. Because the electron distribution is spread over the entire molecule at lower energy, and they're very, very stable molecules. Now, we're going to learn later how to tell whether a non-benzene molecule is aromatic, because aromaticity adds to stability. And if you can determine whether it's aromatic versus non-aromatic, then you can determine its reactivity. Now, you can say something about the reactivity. But benzene is definitely aromatic. And any side groups on that, as long as they don't destroy this conjugated system, then the molecule is still aromatic with those side groups on it, those functional groups. So we establish the root is benzene. And then we say what's attached to the ring. The numbering system on the ring is going to give the lowest locator number to each successive substituent. So this is fairly simple. If you have more than one substituent on there, then you want to use the numbering system that gives you the lowest numbering, the lowest numbers for all the substituents. Okay, so here's an example. Let's take this molecule and let's go ahead and use this example. And the double bonds are different. Now, let's start over again. Make it bigger. Okay. And we got a double here. That means there's one there and one here. We've got a ethyl group there. We got a chloro here. And we have a nitro here. Okay. So which would give us the smallest numbering system? Well, if we went 1 here, then we wouldn't want to go 2, 3 here. We'd want to go 2 here. That gives 1, 2, 3, 4, 5. So this proposed would be 1, 2, 5. If we went here, 1, 2, 3, 4. So we need to go back the other direction and decrease the number from 125 to 1, 2, 3, 4. That will give us the lowest numbering system for this one. Okay. So we've got benzene as our root, right? And we've got 1-chloro. All right, let's do the alphabetical already. This is going to be a methyl. Ethyl. It's going to be an ethyl group. 2 carbons at 4. This is going to be a 2-nitro, and this is going to be a 1-chloro. So alphabetical, it would be 1, 4, 2. So this would be 1-chloro, 4-ethyl, 2-nitrobenzene. That's what I think. 1-chloro, 4-ethyl, 2-nitrobenzene. Okay. All right. If we have a di-substituted benzene molecule, this is you'll see this. I think this would be included as a trivial name. The IUPAC, the systematic name for that first one would be 1-bromo-2-chlorobenzene. That would give you the smallest numbering system, and put them in alphabetical order. And then if we move the substituents, that the 1-2 position is ortho. Ortho is, I don't know if it's Latin or Greek, but ortho means straight. So you go from the 1 carbon straight to the 2 carbon, and there's the other substituent. That's the way I look at it. Then if it's in the 1-3 position, it's meta. I don't know what that means. But the 1-3 position is meta. And para usually means alongside or with. But the para position is opposite. So we abbreviate with the O, M, or P. Right, so 1-bromo-2-chloro will be ortho-bromochlorobenzene. And the meta would be meta-dibromobenzene and para-dinitrobenzene. So this is the ortho, meta, and para positions. Okay. Let's see. Now, if for some reason the benzene ring needs to be a substituent rather than the central ring, and we're going to have to find out what the rules say about that, then the prefixes for the pure benzene ring that's attached directly to the main chain is a phenyl. So when it says phenyl or pH substituent, that means the benzene ring and no additions to it. It's just the benzene ring. If there's a carbon in between, then you could say phenyl methyl, but usually we say benzyl rather than methyl. So let's see where we could use those. All right, so in this case, in that first case, we're going to give priority to the longest chain with a double bond in it. Right? That's the 7-member chain at the top that has that one double bond, and it occurs at the number 2 position. And the phenyl is directly bonded to that 3rd carbon, so it's a phenyl group. That's 3-phenylhep2-ene. And it shows you other ways of representing it. You can write the C6H5, or you can write pH for phenyl. Either way is correct. Now, how about the bottom one? Right? We've got that cyclohexane, and then we've got 2 benzyl groups on it. Well, in this case, you just have to pick one and include the, that, why don't we call one of those, it would be unwieldy. For that bottom molecule, if we said benzene as a root, then how are you going to name the rest of it? That would become a real bear. So I think that's why we start with cyclohexane, because we've got 2 benzyl groups in the pair of positions. 1,4-dibenzyl cyclohexane. That makes sense to me. Any objections? Okay. All right.